Alrighty guys, let's take a look at this web work problem. So this one says RB's greatest basketball player Jack passes a basketball that is initially at rest. The net force on the ball over time is shown below in the graph. The ball has a mass of 1.1 kilograms. Let's pay attention to units and prefixes. Awesome, so we see right here that we have a force versus time graph. You see that force is in newtons and time is in milliseconds. So first thing we need to know is what the force versus time graph tells us. Well, the area under the curve of a force versus time graph is going to give us the impulse, which is the change in momentum. So if we look at our questions below, how does the basketball's momentum change between 0 and 10 seconds? So 0 to 10 seconds, it's on the x-axis, which means that there's no area under that curve, which means that there is no change, so this is going to be constant, meaning that it's not changing. How does the basketball's momentum change between 10 and 20? So 10 to 20, there's a positive area under the curve. So because it's positive, it's going to have a positive change, which means it's going to increase. Next, how does the basketball momentum change between 0 and 20 seconds? So we know 0 to 10 nothing's happening, but from 10 to 20 it is increasing. So the overall change is going to be an increase, because like I said, from 0 to 10 nothing, but 10 to 20 it increases, so overall we have an increase. What is the ball's change in momentum from 0 to 20 milliseconds? So like we said, the change in momentum is talking about the area under this curve. So if we look at this graph really quick, we can see that the only place where there is area is from 10 to 20 milliseconds. So we need to figure out what the area is under this curve really quick. This right here is the only area that we have, and if we look at it, it looks like it's a triangle, and we know that the area of a triangle is just equal to half the base times the height. So let's figure out what the base is. Well, the base is from 10 to 20. So the base in this case is going to be 20 minus 10, which is really just 10 milliseconds. We're gonna have to convert that to seconds, so to convert it to seconds, divide by 1000, so you find out that your base should be 0.01. Now let's take a look at the height. Well, the height is going to be up here, so how tall is our triangle? Our triangle is 20 newtons tall. Now that we have all this information, we can just plug it in, so that means that the area under this curve is going to be equal to 1/2 our base, which is 0.01, and our height, which is 20. If we do the math here, we should end up with an area equal to 0.1 kilograms times meters per second. This area under the curve is talking about our change in momentum, so this should be 0.1. Next, it asks for the impulse between 0 and 20 milliseconds. So again, impulse is the same as change in momentum. This is just asking the same question to make sure you're paying attention. So this is also 0.1. Next question says, what is the ball's velocity at t equals 10 milliseconds? So velocity, in order to figure that out, we need to think about momentum, and we know that momentum is equal to mass times velocity. It tells us that the ball is initially at rest, so that's telling us that the initial momentum in all of these cases is just going to equal 0 if the initial velocity is 0. That's really going to help us figure out what the velocity is at 10 milliseconds, because we know that impulse is equal to final momentum minus initial moment, but we just said initial momentum 0, so this is really telling us that for this graph our impulse is just equal to our final momentum, and like I said before, final momentum is really just equal to mass times final velocity, so all we have to do is figure out the area under the curve from 0 to 10 seconds. Well, 0 to 10 seconds. There's no area under the curve. Since there's no area under the curve, that means that there's no impulse. If impulse is 0 and our initial momentum is 0, then our final momentum needs to be 0. So in this case, the ball is not moving for the first 10 millimeters. What about 20 milliseconds? Well, in this case we do have some impulse, and the impulse here, like we said up above, is 0.1. If I plug that into my equation, I get 0.1 is equal to the mass of the ball times my final velocity, divide by the mass, and I should be able to get the final velocity here. In my case the mass is 1.1, so if I did 0.1 divided by 1.1 I find out that the velocity of the ball at this point should be 0.09, and that's all there is to it. We just need to realize that when we're given a force versus time graph we need to take the area under the curve to get the impulse, and the impulse tells us the final momentum minus the initial momentum. We know that it's increasing when it is positive, we know that it's constant when it's just on the x-axis like so, and it would be decreasing if the line was under the curve, so therefore negative.